For experiments 2 and 3, we're going to attempt to determine an equilibrium constant for the reaction between iron 3 ions and thiocyanate ions, which form the complex ion FeSCN2+. Now, we've discussed how you calculate an equilibrium constant. You have to determine the equilibrium molarities of all of the reactants and products that are in your reaction container. And usually what we do is we start with a system that contains only the reactants. We allow the system to reach equilibrium, and then we determine the equilibrium concentrations. So thinking back to how we do this, we're going to have some known concentration of iron 3 ions placed into a container. We'll have a known concentration of thiocyanate ions also in the container, and we'll assume we won't have any complex ion initially. To reach equilibrium, some amount of the iron ions will react away. We'll call that X. And because it's a 1-to-1 ratio in the balanced equation, we'll have an equal molarity of the SCN react. And because it's a 1-to-1-to-1 ratio, we'll have the same amount of FeSCN produced. So the equilibrium molarities will be the known initial amount minus X, the known initial amount minus X, and then X for the molarity of the product FeSCN2 positive. An equilibrium constant is just the ratio of the molarity of the products to the molarity of the reactants, showing that algebraically we get the equilibrium constant expression, concentration of FeSCN2+, divided by the product of the concentrations of Fe3+ and SCN-. These are their equilibrium concentrations, and so the Kc will equal the equilibrium molarities of each of those species, and we're going to try to determine the equilibrium constant Kc for this reaction in experiment 3. But in order for us to be able to do that, we have to be able to calculate what X is. And the way we're going to find out what X is has to do with the product in this chemical reaction. The FeSCN2+ complex ion actually has a blood red color when it's dissolved in water. That's going to help us to determine X, because it turns out that the concentration of a colored component is always proportional to the amount of light it absorbs. And so we're going to try to measure how much light an equilibrium solution absorbs so we can know what the concentration of the FeSCN2+ is in that solution. Now, making sure we understand the concept, if I have FeSCN2+ in 5 different solutions here, you can see that the one on the left is the lightest, the one on the right is the darkest. What does that mean? Well, the darker color means you have a higher concentration of that colored component, in this case, the FeSCN2+. So the darkness of a solution can be determined by measuring the amount of light absorbed by the solution, and that's called its absorbance. And a solution's absorbance is directly proportional to the concentration of the colored component. So if we can measure the absorbance, we can get a reading for what the concentration is of that colored component. Now, how are we going to measure absorbance? We're going to measure absorbance with a device called a spectrophotometer. It measures the amount of light absorbed by a particular sample. Spectrophotometers always have some type of light bulb that emits white light, which you may recall is a combination of all the different colors of the spectrum: red, orange, yellow, green, blue, purple, violet, indigo violet I meant. What happens in the spectrometer is the light is emitted. There's a wall with a little slit in it. The light passes through that slit. That's how you form a beam. So we get a beam of light. The beam of light then will come across a prism, where the prism is going to break that white light up into all of its constituent rainbow colors. And then we'll have another barrier with a slit that you can actually adjust up and down so that you can actually allow one specific color to pass through that slit. So we're going to actually take the white light and narrow it all the way down just to a couple of different wavelengths, maybe 650 and 651 nanometers, to pass through that slit, so it'll be a particular color. This particular colored wavelength will impinge upon our sample, and if we know the intensity of the light we're shooting at the sample, and then we can measure with the detector the amount of light or the intensity of the light that passes through, we can determine how much gets absorbed. That's what happens in a spectrophotometer. So if you choose a specific wavelength of light to use, in this case, the example we showed was kind of like a blue light, and we pass that blue light through the sample, and the spectrophotometer measured the absorbance of the FeSCN, and we do this for a number of different solutions, we can graph the absorbance that we measure versus what the concentrations of the FeSCN2+ solutions are. So for example, if I have 4 solutions and I know their concentrations of our colored component FeSCN2+, 0.25 molar, 0.50 molar, 0.75 molar, 1.00 molar. I take each of those 4 test tubes, I place them into the spectrophotometer, I measure the absorbance for each of those, and we get some absorbance values. And at least notice at this point, the lowest concentration, the 0.25 molar, has the lowest absorbance, 0.241, and the highest concentration has the highest absorbance, 0.961. That's what we were saying, that the concentration of the colored component is going to be proportional to its absorbance. Well, if we actually take these concentrations and these absorbances and we make a graph, we will find that the relationship between absorbance and concentration is a perfectly linear relationship. If it's a linear relationship, that means absorbance and concentration are going to be related through y equals mx plus b. So this is a linear relationship, y equals mx plus b, where y is going to be the absorbance and x is going to be the concentration of the colored component. So if we wind up making a graph, and we're going to actually produce a graph on our program called LoggerPro, where it's going to plot each of the absorbances we get for each of the solutions of known concentration. LoggerPro will give us the equation of the best fit line for those points, which is written at the top here in the graph. It says A at 476.0 equals mx plus b. It's telling you m is 3,425. It's telling you b is negative 0.021. So we're going to have a relationship between absorbance and molarity. This is the whole point of experiment 2. We're going to try to get this particular graph showing us the relationship between absorbance and concentration. Why are we doing that in this experiment? So that in experiment 3, we can determine the equilibrium constant for this reaction. Thinking back to the ice table we talked about before, if we want to get the equilibrium constant, we need to know the equilibrium molarities, so we have to know the value for x, and the graph that we have on the left side of the slide is going to allow us to determine what x is. Let's say we take an equilibrium solution that has iron 3, thiocyanate, and the complex ion FeSCN2+ in it. We put it in the spectrophotometer, and we read the absorbance. So let's say an equilibrium solution has an absorbance of 0.351 using a wavelength of light of 476.0 nanometers. Find its concentration of FeSCN. So the equation for this line is going to tell us how to do that. The absorbance at 476, and when they put that A at 476, they're just specifically saying that we're doing the absorbance of the wavelength of 476 nanometers. It actually says on LoggerPro A-476, and I don't want you to get confused to think the left side of the equation is A minus 476. They're just telling you what wavelength of light they used to measure the absorbances. So that absorbance value is going to equal mc plus b, where c is the concentration. That's what we're going to try to solve for. So the absorbance at 476 nanometers for our solution was 0.351. The slope from the graph on the left side of the slide is 3,485. Now I have the units of molarity to the -1. We've talked about graphing before in activity 1. When you're calculating a slope is difference in y's over difference in x's. On our graph here, the y values are absorbances, the x values are concentrations. Absorbances have no units. Concentration in this case is measured in terms of molarity. So our slope is going to have no units over molarity, and the simpler way to write that is molarity to the -1. So that's where I got my units of molarity to the -1 for my slope. So all we have to do now is solve this for C. That's going to be the concentration of the colored FeSCN2+ that's producing this absorbance of 0.351. And so I'm going to add 0.021 to both sides of the equation, and then I'm going to divide by 3,425 molar to the -1. And then when I do that, the units, the molarity will flip to the top, and we're going to get a value of 0.000109 molar. So that's the concentration of the FeSCN. Therefore, that's its concentration at equilibrium, that's X. And then if we know the concentrations of the two reactants, we take their known concentrations, subtract the X value we have here, we'll be able to calculate the equilibrium constant. So that's really where we're going. Today's experiment is only to calculate the calibration line that we have on the left side of the slide so that we have a linear equation that we have the equation for to be able to relate absorbance with concentration. And then experiment 3, we'll make equilibrium solutions, and then using our calibration line, we're going to find the values for X, and we'll wind up calculating the last line in our ICE table, which are the molarities of all the reactants and products. So in today's experiment, part A, you're going to prepare something called a stock solution. It's going to be a stock solution of the colored component FeSCN2+. A stock solution is a solution of known concentration. In this case, we're going to know the concentration of FeSCN2+. And as you watch the lab, you're going to see that the way we're going to produce this stock solution is by mixing 10.00 milliliters of 0.200 molar iron 3 nitrate with 3.00 milliliters of 0.00200 molar potassium thiocyanate, and then 17.00 milliliters of 6 molar nitric acid. When we put these together, the iron ions and the thiocyanate ions will react together to form FeSCN2+, which is a colored complex ion, so the solution will turn a light form of the blood red color. The question is, what's going to be the concentration of the FeSCN2+ in this solution, which is our stock solution? So I'm going to show you how we do that calculation now. So in your data table for part A, let's go through the entries. The first one says, what's the concentration of FeNO3 taken 3 times used to make the stock solution? That's what we showed you on the last slide. It was 0.200 molar. What volume of the iron 3 nitrate solution are we going to use to make the stock solution? We're going to use 10.00 milliliters. What's the concentration of the potassium thiocyanate used to make the stock solution? From the previous slide, it was 0.00200 molar. What was the volume of the potassium thiocyanate used to make the stock solution? We used 3.00 milliliters. Then, what's the volume of the stock solution? Well, we're mixing 10 milliliters of the iron 3 nitrate solution with 3 milliliters of the potassium thiocyanate solution, and then with 17 milliliters of nitric acid. That adds up to 30 milliliters altogether. So the volume of the stock solution we're going to produce is going to be 30.00 milliliters. Now, with numbers in the left margin, these are calculations, and there will be a corresponding calculation box for you to do the work in after the data table. So after the data table, look for box 1. That's where I want you to show the calculation of your concentration of FeNO3 taken 3 times in the stock solution. So to do this calculation, we're starting with a iron 3 nitrate solution that's 0.200 molar, and we're going to add a whole bunch of other solutions to it. And whenever you do that, you dilute the solute. So the 0.200 molar of iron 3 nitrate is going to go down as it's diluted. And so in box 1, to do a calculation like this, when you're diluting the concentration of a solute, we use our dilution equation. MCVC, the molarity of the concentrated solution, which means the initial solution, times the volume of the concentrated or initial solution, will always equal the molarity of the newly created diluted solution multiplied by the volume of the diluted solution. So let's see if we can identify each of the variables. The initial solution that contains iron 3 nitrate is going to be 0.200 molar. The initial volume of that iron 3 nitrate solution, how much of it we're using to make our stock solution, was 10.00 milliliters. What we're solving for is what's its molarity going to be once we've mixed it to a final volume of 30. So I don't know its molarity in its diluted form, but I do know the volume in its diluted form. Its volume is going to 30 milliliters. So all you have to do is take the dilution equation at the top and solve it for m sub d. So I'm going to multiply 0.200 molar multiplied by 10.00 milliliters divided by 30.00 milliliters. I don't need to switch the milliliters into liters because whether I do milliliters divided by milliliters or liters divided by liters, it's the same ratio. Milliliters just cancel out. My answer will come out in terms of molarity, and I get 0.0667 molar iron 3 nitrate. So we're preparing a stock solution that is going to be initially 0.0667 molar of iron 3 nitrate. Second calculation, concentration of potassium thiocyanate in the stock solution. We're going to do that exactly the same way. We're going to be diluting the original potassium thiocyanate solution, so now the concentration of the potassium thiocyanate is going to be less. So in box number 2, we're going to use the dilution equation. What are we starting with? For the potassium thiocyanate, we're starting with 0.00200 molar. That's the initial or the concentrated molarity. How much of it are we using? We're using 3.00 milliliters. We want to find out what its diluted molarity is going to be, and the final volume is going to be whatever the 3 milliliters are when you mix it with 10 and 17, which is going to be 30. So the final volume is going to be 30. So solving for the molarity of the diluted solution in the same fashion as we did before, we go 0.00200 molar, multiplied by 3.00 milliliters, divided by 30.00 milliliters, and that gives us a molarity of the potassium thiocyanate of 0.000200 molar, and we enter that into the data table. Third calculation. What's the concentration of the iron 3 ions in the stock solution? So this is more of a conceptual question. We know that the solution is now going to be 0.0667 molar in iron 3 nitrate. We calculated that, calculation number 1. This is an ionic compound. When ionic compounds dissolve in water, the ions separate from each other. And because the iron 3 nitrate only has 1 iron in its formula, then for each iron 3 nitrate formula unit that dissolves, you're going to get 1 iron ion in the solution. If you have 100 of them dissolved, you're going to get 100 iron 3 ions. If you have 0.0667 molar iron 3 nitrate, when it dissociates, you'll have 0.0667 molar of iron 3 ions because there's 1 iron 3 per formula unit. You could write this out if you wanted to express that in terms of dimensional analysis. For every 1 mole of iron 3 nitrate you put in the denominator, there'll be 1 mole of iron 3 ions. It's a 1-to-1 ratio. So the molarity of the iron 3 ions are just going to be 0.0667. You essentially really don't need to do a calculation. You just have to realize it's the molarity of the compound multiplied by the number of iron ions in the formula, which is 1, 0.0667. Calculation number 4, what's the concentration of the thiocyanate ions in the stock solution? So this is now going to be a similar calculation. We know that in the stock solution, the potassium thiocyanate is 0.000200 molar. So what's going to be the molarity of the thiocyanate ions? There's 1 thiocyanate in the formula. So every time 1 KSCN dissolves, you get 1 SCN minus ion. It's a 1-to-1 ratio. So just multiply 0.000200 by 1. Specifically, you're actually multiplying by 1 mole of SCN minus over 1 mole of KSCN. That turns out to be 0.000200 molar of SCN minus. We now know that molarity. The last thing we're now going to have to determine is what's the equilibrium concentration of the FeSCN2+ in the stock solution. Because really all we've calculated now is the initial concentrations of the iron 3 ions and the thiocyanate ions, but they're going to react to form FeSCN. So now we have to figure out what's the equilibrium concentration of the FeSCN. So watch how we do this. This is kind of tricky. The concentration of the FeSCN2+ in the stock solution, which means its equilibrium concentration, is going to essentially come from an ice table. So what we have in our stock solution before we assume any reaction occurs, as we've just deduced, it's 0.0667 molar of iron 3 ions, and it's 0.000200 molar of SCN minus, and before they react, there won't be any of the complex ion. Some unknown amount of the iron 3s will react, but they'll react in an equal ratio with the SCN minuses to form an equal amount of FeSCN2+. So the equilibrium molarities will be 0.0667 minus X, 0.000200 minus X, and then X. How do we figure out that X? Here's the key. Look at these two numbers. 0.0667 is way bigger than 0.000200. So we actually have 333 times more iron 3 ions than thiocyanate ions. Because it's such a discrepancy, we're going to make the assumption that essentially all of the thiocyanate gets reacted away into FeSCN. So I'm going to erase my bottom 2 lines in my ice table, and I'm going to assume that approximately all of the SCN will react away because it's such a small amount. Now it has to react in a 1-to-1 ratio with the iron 3 ions, so this is going to be about 0.000200, and it's a 1-to-1-to-1 ratio, so this has to be plus 0.000200. So we're going to have some amount of iron 3 ions in there at equilibrium, which are not going to contribute to any color. We'll have essentially no SCN minus, but here's the key. We're going to assume that we have 0.000200 molar of FeSCN in the solution at equilibrium. So here's the key. We've made the SCN initial concentration so small that we can make the assumption that it completely gets converted into FeSCN2+. So whatever the molarity of the SCN minus is in our stock solution, that will be the molarity of the FeSCN2+. So we're going to assume they're equal, and therefore it's 0.000200 molar. So in your data table at the very bottom, we'll assume that all the SCN gets converted into FeSCN, and so its concentration will be 0.000200. That's part A. That's going to be the concentration of the FeSCN in this 30 milliliters of stock solution that we've prepared. Now, what do you do with the stock solution? You take a stock solution and you dilute it to make solutions of lower concentrations. So in part B, we're going to prepare what are called the standard solutions of FeSCN2+ from the stock solution. And we're going to actually prepare 6 solutions. Solution 0 is one that does not have any of the colored FeSCN in it, but the other ones all do, and they have varying amounts of the colored FeSCN being mixed with varying amounts of colorless nitric acid. But if you notice, each of the solutions, the total volume will always add up to 5. So we have to calculate the concentrations of the FeSCN2+ in all 6 of these solutions, and then we're going to enter those values into the data table under parts B and C. This is where the concentrations of FeSCN2+ are going to be placed. So we're going to calculate those. We're not measuring those. So first, for solution 0, because solution 0 has no colored FeSCN2+ in it, therefore the concentration of the FeSCN+ in solution 0 is going to be 0. So over in the data table for standard solution 0, which I've listed at the bottom, you can put 0. For solution number 1, this is made of 5 milliliters of the stock solution, and we're mixing it with nothing else. So we're not diluting it. Its concentration doesn't change. So whatever the stock solution's concentration of FeSCN was, that will be the concentration of FeSCN in solution 1, which is 0.000200 molar. So for solution 1, you place that. Now, all the other ones, solutions 2, 3, 4, and 5, we're mixing some of the stock solution with some colorless nitric acid. So therefore, the molarity of 0.000200 is going to get lowered as the solutions are diluted. So you're going to have to calculate the actual molarity of the FeSCN in solutions 2, 3, 4, and 5 by using the dilution equation, MCVC equals MdVd for each of them. And I'll let you go through those particular calculations, but that's how that's going to be done. You need to have all the molarities of the FeSCN in each of the standard solutions calculated first, because then we're going to take each of those solutions, we're going to place them into a spectrophotometer, and we're going to read their absorbances, and the spectrophotometer will then ask you what is the concentration of this solution that you're putting in the spectrophotometer, and you have to know what it is. But we will therefore then read these particular values, and then we'll now have absorbances corresponding to concentrations of FeSCN2+. So in part C, we're going to determine the absorbances of the standard solutions, and the way this is done, and this goes through the procedure, you'll see this in the laboratory video, is we're going to first take a colorless solution, which is solution 0, and we're going to place it into the spectrophotometer. This is called the blank because it doesn't have any of the colored component in it, and it allows the spectrophotometer to set its absorbance reading to 0. Once we've done that, we're going to then remove that from the spectrophotometer, and we're going to place a colored solution in there, usually the one with the most intense color or the darkest color. And we're going to try to shoot every single wavelength of light through that sample to try to figure out which wavelength of light our sample absorbs most strongly. So we'll place a colored standard solution into the spectrometer, and then we're going to get what's called an absorbance spectrum. It's going to show us what wavelengths are absorbed after we shoot wavelengths of all of the visible spectrum through the sample. So this is called an absorbance spectrum, a graph of the absorbance of a solution at all different visible wavelengths. Now, the solution we're dealing with has, in a dark form, a blood red color. A little bit lighter form, it's going to look orange. So if a solution appears orange, the reason for that, a little bit of physics here, is that it's absorbing its complementary color. If you take all of the regular colors, red, orange, yellow, green, blue, and violet, put them into a circle, complementary colors are located directly across from each other. So if you have an orange colored material, it's orange because it's probably absorbing a lot of blue light, Look at our graph here. For our orange sample, what's it absorbing? It's absorbing blue light. The peak is right there in the blue part of the spectrum. So the wavelength that shows maximum absorbance, the one with the highest value in terms of absorbance on our full spectrum graph, is called lambda max. It means the wavelength of maximum absorbance. So here's the peak of the absorbance graph right here. So just read down to the bottom onto the x-axis and you're going to get lambda max. So we're going to wind up using this particular wavelength to do our analysis, because when measuring the absorbances of solutions, you always get the most accurate result if you use the wavelength that it absorbs the best. And that's what lambda max is telling you. So this comes out something like 476 nanometers or something. So we're going to actually enter that into the data table at the very top, because when you come back for experiment 3 and you're going to use your spectrophotometer again, you want to make sure you're using the same wavelength next experiment as you use this experiment. So you'll enter in there the wavelength of maximum absorbance, whatever it happens to be for you. It'll probably be in the high 400s. Now, what we're going to do is we're going to determine the absorbance of each standard solution at this wavelength max. So we have 4 or 5 or 6 different solutions. We'll place them into the spectrometer. We'll read the absorbance. We'll tell it what the concentration is. And then Logger Pro will be able to make a graph of the data. So in my little example here, I'm using 4 solutions, 4 different concentrations, and we've measured their absorbances in green right below them. So when Logger Pro graphs that data, and we ask it to give us the equation of the line of best fit for those points, we'll get our equation, which is written like this: A at 476.0 equals mx plus b. They tell you m is 3,485 and b is negative 0.021. And the r squared at the bottom is just a statistical tool to tell you how close you are, in this case 5 points are, to making a perfectly straight line. If they're a perfectly straight line, the r squared value is 1. And so if you're close to 1, specifically for us, greater than 0.95, that means the data points are actually pretty good. So 0.995 is actually some good correlation between our 5 points. So experimentally, we did a good job. So this line is called a calibration line because it's showing us the relationship between the measured absorbance and what the concentration of the FeSCN2 plus is in the solutions. So they follow this equation, y equals mx plus b, so we can say what's on the y-axis, the absorbance at a wavelength of 476 is going to equal the slope, 3,425 molar to the minus 1, multiplied by the concentration of the colored component, minus the intercept, which should be close to 0, and it comes out minus 0.021, which is actually pretty close to 0. So we'll actually wind up using this in our next experiment. So when we calculate the absorbance of an equilibrium solution, we'll plug that absorbance into the left side of the equation, and it'll allow us to solve for C, which will be the concentration of the FeSCN in that equilibrium solution. Now, when you get your calibration, your equation for your calibration line, you want to make sure you place that in your data table, because we're going to need to have that equation when we go to experiment 3. And so that goes in the last line of the data table here in parts B and C. You want to make sure that's entered in that data table. Now, a little bit of theory behind this relationship between absorbance and concentration. In 1852, August Beer proposed a mathematical explanation for the linear relationship between concentration and absorbance. This is the equation we've been dealing with so far today. The absorbance of a sample equals slope multiplied by its concentration plus B. And Beer proposed that the slope of this line is actually the product of 2 things. The first variable epsilon, the second L. And we actually call this today Beer's law. Absorbance equals epsilon times L times C. Technically, you would say plus 0 because the intercept's supposed to be 0, but they usually just leave that out. So this is called Beer's law. What do each of the variables stand for? A is the absorbance. The epsilon is called an extinction coefficient. It's a coefficient, and its numerical value is dependent upon what wavelength you use. So it's a constant for a given solute, whatever solute you're using. In this case, FeSCN2 plus is the colored solute, at a specific wavelength. So if you use a wavelength of 476 in experiment 2, then if you want Beer's law to work, you have to use the same wavelength in experiment 3. Otherwise, epsilon will be different, which means your slope will be different. So if you want to use your equation with a particular slope that you're calculating from Logger Pro, You have to make sure you use the same wavelength of light because that will actually affect the slope. L is the width of the cuvette, which is the container that holds our sample that we place into the spectrometer. And it turns out that our cuvettes are all 1 centimeter across. So therefore, the value for L in our experiments will be 1.00 centimeters. And then C is the concentration. You can actually measure concentration in any units you want. You can have mass percent, you can have molarity, you can have molality. In this case, it's going to be the molarity of the FeSCN2+. Now, the significance of Beer's law is that sometimes people will want to know what the extinction coefficient is, and let me show you how you get that. To calculate the extinction coefficient for the absorbance at a wavelength of 476 nanometers and using a 1.00 centimeter cuvette, given the calibration line, absorbance at 476 equals 3,425 molar to the -1 times concentration minus 0.021. So how would you get an extinction coefficient from this equation, which is something that would appear on Log or Pro after you do an analysis to do a calibration line? Well, the absorbance is what's graphed on the y-axis, concentration is what's graphed on the x-axis, and what's in front of the concentration, the 3,425, that's the slope. And really, that's all that's important, because what August Beer said is that slope is epsilon times L. And so if we only use this fact here, the slope must be epsilon times L, we can solve for the extinction coefficient, because I can see the slope right here on the slide. It's 3,425. I know what L is, unless you're going to bring your own cuvette from home and it's a different size. The cuvettes we have are always 1.00 centimeter. So the way you calculate an extinction coefficient is you just divide the slope by whatever the path length is for your cuvette. So in our case here, the slope was 3,425 molar to the -1. The path length was 1.00 centimeters. So dividing this, we wind up getting a 3 significant figure number because my denominator was only 3 significant figures, 3,430, and the units would be molarity to the -1, centimeters to the -1. So that would be the extinction coefficient for FeSCN2+ using a wavelength of 476 nanometers.